Hello, and welcome to this Richardson RFPD webinar. My name is Katie, and I will be your Global Spec moderator, and I would like to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today's webinar. Just to the right of the main presentation window is the Speaker Bio window with background information on today's presenters. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now a quick word about Richardson RFPD. Richardson RFPD, an aero company, is a specialized electronic component distributor providing design engineers with deep technical expertise and localized global design support for the latest new products from the world's leading suppliers of RF, wireless, IoT, and power technologies. Now let me introduce today's presenters. With us today is Bernie Gobe. Bernie is the VP of Business Development at Signalcraft Technologies. Also joining us today is Lauren McClellan. Lauren is a product manager at Signalcraft Technologies. And we also have Razvan Rusu. Razvan is the Director of Global Engineering at Richardson RFPD. To read more about any of our presenters today, please look at the Speaker Bio window right next to the main presentation window. And with that, I'd like to pass things along to Razvan to get this webinar started. So go right ahead.
Hello, everyone, and thank you for attending our webinar. My name is Razvan Rusu, and I am the Director of Global Engineering at Richardson RFPD. In the first part of our 45-minute long presentation, I would like to cover the objectives of our design, give you a brief feature set overview, touch a little on targeted market segments and applications, and end with one of the many use cases as an example. Then I will turn it over to our design partner, Signalcraft Technology, and allow Bernie and Lauren to do a deep dive into the design details and challenges, share test data, and play a short unpacking video with details on the steps required to configure the product. For those in the audience who weren't previously exposed to Richardson RFPD, I'd like to start by saying that we've been serving customers in the RF and microwave field since 1947. Richardson RFPD is the largest RF and microwave component distributor in the world, with a team of over 150 customer-facing sales engineers and applications engineers deployed in all major markets. Other technology segments that we serve at RFPD include power electronics, with a huge emphasis on renewable energy and industrial IoT. As of March 2011, we have become a wholly owned subsidiary of Aero Electronics. About 5 years ago, we introduced the concept of design accelerators, which essentially are system-level platforms that incorporate leading-edge technology from our suppliers. The idea was to enable the system or design engineer with better tools that would allow them for quick evaluation and provide them with the shortest path to prototyping. The first family of design accelerators we introduced to the market was a series of RF front ends that, when paired with software-defined radio platforms, would create a complete development communication system for applications below 6 GHz. The second was a line of software-defined radio system on modules developed around the latest and greatest integrated transceiver technology from Analog Devices. That family was launched at the end of 2021. Information on both could be found on our website. Today we are going to introduce a new design accelerator family, our first product of the frequency converter line, brand name RadioThorium, and focus entirely on this first edition, which is a 24 to 44 GHz frequency converter. The product was designed with the best performance cost trade-off option in mind, but it was meant to satisfy stringent RF performance requirements such as large signal instantaneous bandwidth support, exceptional linearity, and low power consumption. As far as availability goes, Richardson RFPD will be the exclusive channel, and the plan is to have product on the shelf by the second quarter of 2022. We are already planning on future additions to complement the first release, with the goal of providing the RF and microwave community with a broader spectrum of frequency converter options from DC to 60 GHz. Millimeter wave design is inherently complicated, and when combined with power generation, distribution, processing, and control, it becomes even more challenging. The RadioThorium frequency converter includes everything I just described: an onboard processor, high-performance RF signal chains. In fact, it could be considered a system in itself. But as we all know, a frequency converter would always coexist and interface with a digital baseband platform, either a dedicated SoC or an FPGA, an RF front-end, or an antenna array to complete a full communication system. With that concept in mind, our design objectives were very simple. The unit has to be easy to use. The user will only need a power adapter, which by the way is included in the kit, to turn on the unit and get going. Out-of-the-box experience is key to us. Simple demo scripts will be provided, as well as proper and intuitive console command documentation. Flexibility. Our unit is full of features. It will provide the design engineer with different ways to configure and program it, create MIMO configurations by stacking up multiple units if needed. It will have options like onboard LO and frequency reference generation, as well as the option to inject external LOs and synchronize from an external reference, and many, many other features we are going to touch later on this presentation. Availability. What we are promoting isn't a paper design. Our commitment to our customers is that we will have enough inventory at Richardson RFPD to address demand. Everybody knows we are in the midst of a global semiconductor shortage. Components and evaluation boards are difficult to procure in a timely manner, so our vision is that getting evaluation hardware in the hands of our customer from inventory, while assuring that all critical components that we use in our design are also available, it is a very powerful proposition. Finally, the ultimate goal is not only to enable, but also to shrink the design cycle by 6 to 12 months and reduce our customer time to market by mitigating design complexity and risk. I will quickly go over a few examples of markets and applications that we believe we can target with our RadioThorium design. The most obvious one is the millimeter wave commercial communication systems, including infrastructure 5G deployments in bands N257, 258, and 261. Our product will in fact cover all 5G millimeter wave bands in the 24 to 40 GHz spectrum, including band N260 from 37 to 40 GHz. That was initially available in the USA, and it is now available all around the world. Integration with dual polarization, high element count antenna arrays is one of the many use cases that we are promoting. Under commercial communication systems, I should potentially include microwave backhaul point-to-point radio links in the licensed bands from 24 to 42 GHz, which have stringent requirements for linearity, not as much on channel bandwidth support, but in any case, our unit will perform just fine in those conditions. Satellite communication is another market that benefited from access to K-band spectrum and therefore to higher bandwidth communication. One good example that comes to mind are the LEO constellation deployments that went through the roof in the recent years, and here I can list the SpaceX, OneWeb, and Telesat's Lightspeed. Our unit would only cover the SATCOM uplink path from 27 to 31 GHz, but that will take care of both the commercial and military spectrums. RF test equipment market has experienced a tremendous growth in the past years, and it is expected to surpass revenue of $6 billion by 2025. Bench equipment, ATE stations, over-the-air testing of antenna and front ends, harmonic testing for Wi-Fi 6 and 7, and the most common use case, which is frequency coverage extension of traditional test equipment to millimeter wave, are some of the use cases that we see out there. Radar and microwave imaging benefit from the use of K-band in remote sensing, and it creates new opportunities in Earth observation for science and civil security applications due to the unique characteristics of the millimeter wave frequency range. Finally, electronic warfare and electronic countermeasure will always benefit from broadband designs, multi-channel configurations. Few remarks on some of the key features of our design. We're going to touch on some of them and go into more details in the next section. Both the TX and RX signal chains were designed to accommodate applications that require high linearity and large instantaneous channel bandwidths. As part of both TX and RX signal chains, we are providing the user with two different channel filtering options. The first one is an onboard based on a switchable filter bank with a pass-through option, and the second one is external, also based on a programmable filter bank, a unit that we designed to complement the RadioThorium frequency converter and could be cascaded in series. Two microwave wideband synthesizers from Analog Devices provide the main building block for our LO generation circuits. They allow implementation of fractional M or integer M PLLs, have integrated VCOs, and support reference input frequencies up to 600 MHz. They could be disabled or bypassed, allowing for external LO injection for those use cases where lower phase noise is required. Since we have the up converter and down converter chips tied to different LO sources, they could be programmed individually to support TDD and FDD configurations. The front-end switch matrix was designed and optimized to provide the flattest frequency response, lowest insertion loss, and better than 10 dB return loss across the band. The IFTX-RX are single-ended ports, although the frequency range of the up and down converter chips we used in our design should cover 0.8 to 6 GHz for RF inputs. The broadband 900-degree hybrid we use in our circuit limits that range to 2 to 6 GHz. On the baseband INQ ports, filtering should be provided externally if the requirements for channel bandwidth are lower than 1.4 GHz. Finally, our TX chain includes a gallium arsenide p-HAMD power amplifier MMIC that will allow us to deliver a minimum of plus 16 dBm of P1 dB in TDD mode and plus 19 dBm in FDD mode across the band, and that is the output connector level, so it factors in all post-PA losses. This will definitely be sufficient to drive higher elements count antenna arrays up to 256 elements, where multiple layers of splitting and combining are required to feed the multi-channel beamforming ICs. Those power levels will also be sufficient to drive higher power amplifiers, MMICs for applications like SATCOM and EW. Although we haven't gotten quite there yet, our development plan includes testing and characterization with software-defined radio platforms, a task we aim to complete by mid-2022. I just wanted to be upfront and mention that all test data that we will make available in our documentation package or our tech support page will be taken by either using lab equipment or the Analog Devices mixed signal front end, in short, the MXFE platform. Nothing will stop the user to choose a different solutions. However, we do not have any short plans for characterization with a different SDR, perhaps in the future. The MXFE is the perfect option for system designers working in communication infrastructure, instrumentation, and aerospace and defense. It provides with a scalable SDR solution with bandwidth up to 7.5 GHz, and it greatly simplifies the signal change complexity. The MXFE offers smart integration of RF ADCs and RF DACs with on-chip digital signal processing and clock and PLL for multi-chip synchronization. In the middle, I have a very simple diagram that shows a 2x2 MIMO system built out of an MXFE standard evaluation board and two of our RadioThorium units. Operation is possible in both IF or baseband INQ modes to create a millimeter wave system that will only require a front end to be complete. The two RadioThorium frequency converters could be controlled from a single host and could be phase synchronized with the MXFE board. In those cases where the requirement for instantaneous bandwidth is less than 200 MHz, a better option could be analog devices integrated transceivers that are available in dual and quad channel configurations. However, the transceiver will only serve as an IF stage and it won't be able to operate in baseband mode when interfaced with our RadioThorium frequency converter. I have few options here that include the ADRV 9008-1 and 2, which is a transmit-receive combo that was released a few years ago, and the most recent release, the ADRV 902X series, that includes 4 TXRX channels and supports central frequencies from 75 MHz to 6 GHz. I'm going to conclude with a slide on a 5G use case. In this block diagram, we are showing the analog device's MXFE connected to the RadioThorium frequency converter, driving a 5G antenna system. The FPGA board is the ADS9, and it is part of the standard hardware evaluation toolbox of the MXFE. This configuration will enable the user for any type of characterization from a CPE type of configuration with 16 antenna elements all the way to a base station grade that could include up to 256 elements. The user has also the flexibility to implement antenna array calibration algorithms in FPGA or even perform array predistortion in FPGA if needed. For dual polarization configuration, 2 RadioThorium units will be required. Support for up to 4 units is available without any software changes. The frequency converters could be phase synchronized and controlled via SPI by the antenna system or the FPGA board. Another feature that we offer is that the DC power could be shared from the RadioThorium unit with the antenna system or the rest of the system. Our unit includes an unused rail regulated power supply that could be shared in those situations that call for pulling DC out of our box to power the antenna array, which gives the user more flexibility. And with that, I'm going to end the intro section and turn it over to Bernie and Lauren, who are going to walk you through the fun part of this presentation, focused on the design details. Bernie, it's all yours.
SCT developed RadioThorium in partnership with Richardson RFPD and Analog Devices. Richardson RFPD funded the program and will be the exclusive sales channel. Analog Devices supplied most of the semiconductor content, which included access to new devices. Many companies lack the resources to design and build product at 40 GHz. This compact demonstration platform provides customers with an accelerated path to developing proof of concepts for evaluation and demonstration purposes. It also helps to reduce time to market by mitigating design risk and program complexity. Full customization and product development support is available from SCT. RadioThorium is another building block in our toolbox that we can leverage to help accelerate the development of your millimeter wave projects. SCT developed RadioThorium in partnership with Richardson RFPD and Analog Devices. Richardson RFPD funded the program and will be the exclusive sales channel. Analog Devices supplied most of the semiconductor content, which included access to new device. Many companies lack the design resources to design and build product at 40 GHz. This compact demonstration platform provides customers with an accelerated path to developing proof of concepts for evaluation and demonstration purposes. It also helps to reduce time to market by mitigating design risk and program complexity. Full customization and product development support is available from SCT. RadioThorium is another building block in our toolbox that we can leverage to help accelerate the development of your millimeter wave projects. The millimeter wave converter is a standalone platform for use in the 24 to 44 GHz range. Let's have a look at some of its key features. The module is designed to interface directly with software-defined radios, such as those commonly implemented using analog devices mixed signal front end. Power is provided by a 12-volt wall cube, which is included with the kit. An embedded fan and temperature monitoring are integrated into the unit to manage heat. Control of the module is provided via USB or SPI interfaces. Most users will interact via console over USB. Alternatively, embedded controllers may access the UART or SPI buses available on the secondary control port. Two APIs are available. The first is ASCII-based, and its commands follow the SCPI structure as defined in IEEE 488.2. The second is a binary protocol, targeted at embedded control applications where speed and timing may be of concern. Both protocols are defined in our API specification, which has been posted on the support portal. Up to 4 units can be combined in a vertical stack to create a 4x4 MIMO system. In this scenario, the control bus is routed to the cascaded modules over the expansion port. In this manner, API commands sent on the primary unit can be redirected to the downstream modules. This eliminates the need for multiple controllers and simplifies timing and synchronization between units. Module addresses are set using a dip switch on the configuration port. A third control port is also available. This port exposes power, SPI, and GPIO to provide users with a convenient method of interfacing to external front-end modules, such as integrated antenna arrays and switched filter banks. The low-frequency RF ports, shown on the bottom of this image, include the IF, INQ, external LO, and external frequency reference ports on SMA connectors. The millimeter wave ports, visible on the top of this image, include 2.4 millimeter connectors for the FDD TX and RX functions, in addition to a bidirectional TDD port. This high-level diagram represents the complete radio realized in the converter. We won't dwell on this eye chart, but it's been presented to provide some context for the detailed block diagrams which follow on the next 3 slides. On the left, we can see the shared frequency reference and the 2 internal oscillators. On the far right of the diagram, you may note the connectivity between the up and down converter paths required to support TDD functionality. This diagram represents a simplified view of the up converter block, also known as the transmit chain in RadioThorium. Key blocks implemented with the help of analog devices semiconductors are shown here for reference. The converter can be configured to accept an IF or INQ modulated signals. The IF port supports signals between 2 and 5 GHz. In addition to some programmable gain, an onboard filter bank is provided that incorporates multiple bandpass filters in addition to a bypass path. The filter bank is realized using common 5G devices, varying from 20 to 1400 MHz in bandwidth and centered at various IF frequencies. The INQ inputs provide connectivity to external single-ended DACs operating at up to 6 GHz. A low-pass filter is included to help with alias and spurious rejection. SCT has created a complementary external baseband filter bank, the SC4710, that can be added to the I and Q paths of the system to aid in rejection of spurious signals. Control of this external filter bank is provided over I2C. Power and I2C are available on the secondary control interface of RadioThorium. The up converter incorporates the ADMV 1013. The onboard multiplier reduces the frequency requirements for the local oscillator. The quad mixer provides sideband suppression and reduces carrier feed-through. Multiple configuration registers are available for users that want to tune and optimize overall performance. The ADA-PA 7002 is biased using an onboard controller to provide full tuning of its operating conditions. RadioThorium can be used in either time division duplex or frequency division duplex modes. In FDD mode, the upconversion path has approximately 30 dB of gain, an output compression point of, or P1 dB of 20 dBm at 40 GHz. In TDD mode, the gain is also 30 dB, but the P1 dB reduces to 16 dBm at 40 GHz because of the additional switch in the path. A detailed specification is available on the support portal of SCT's website. This diagram represents a simplified view of the down converter block, also known as the receive chain of our demonstrator. It is essentially a mirror image of the up converter with a few exceptions. Of most significance, the I, F, and IQ paths incorporate significantly more gain than the up converter. The IF path provides approximately 60 dB of gain control, and an additional 19 dB are available in the RF section. Approximately the same amount of gain control is available when operating with the I and Q paths. In FDD mode, the down conversion path has approximately 65 dB of gain, a noise figure of 9 dB, and an input compression point, or P1 dB, of 0 dBm at 40 GHz. In TDD mode, the gain is also 73 dB, noise figure of 9 dB, but the P1 dB reduces to -7 at 40 GHz. Now let's have a look at the local oscillator block. It should be noted that each conversion path has its own LO source to support FDD operation. Each LO can be configured independent of the other, providing users with a complete control of the RF, LO, and IF frequency plans specific to their application. The ADF 4372 was designed for use with the ADMV 1013 and 1014 converters. The synthesizer can generate outputs in the 62.5 MHz to 16 GHz range. Because of the built-in ×4 multipliers of our converters, our LOs are only required to operate at up to 10.2 GHz. Optionally, the onboard synthesizers can be disabled when external LOs are supplied by the user. Both onboard and external frequency references are supported. The reference frequency source is shared between the TX and RX synthesizers. Use of external references are typically required to synchronize with external test equipment. As previously mentioned, several control options are provided to support the wide range of use cases and applications perceived for this demonstrator. The control inputs are shown here on the left-hand side. Benchtop and ATE users will likely leverage the Skippy command line API using a console connection over the USB interface. The same Skippy API is also accessible over UART and will likely be the preferred interface for embedded systems users. Alternatively, embedded users concerned with speed may prefer to use the binary-based API over the SPI port. Control output interfaces are shown on the right-hand side. Power and an I2C bus are available on the secondary control port for interfacing with the optional 4710 external filter bank. Power, GPIO, and an SPI bus are also available on the expansion port for controlling external front ends such as patch antennas or millimeter wave filter banks. Finally, we can point out the expansion port, which is used to control add-on RadioThorium units when cascaded in a MIMO or similar configuration. We've briefly touched upon the console interface, which uses a Skippy-like command set. To simplify interacting with RadioThorium, a series of macros or high-level commands have been defined. These macros assign default configuration settings for many of the onboard registers, reducing the number of parameters required to program the unit. In our example, let us assume that a user desires to set the TX synthesizer output to 10.25 GHz. This process can be as simple as using the SYN_OUT macro with a single parameter. When executed, all SYN registers, such as divide ratios, charge pump currents, and the like, are calculated by RadioThorium. In some applications, however, users may wish to optimize performance for a given set of operating conditions. In these cases, other commands are available that provide users with full access to all onboard registers. In the example above, the SYN_REF set command could be used to access the full divide ratio set available on the synth. Other commands would provide access to the charge pump current and other configuration settings.
So here we have the box for the RadioThorium unit. Opening it up, we see the RadioThorium unit itself along with the DC power supply. So we'll take a closer look at the RadioThorium unit. On the lower side of the unit are the lower frequency SMA ports, which include the IF ports, the I and Q ports, the external LO inputs, and then also a reference clock input. On the upper side, we see the 2.4 millimeter microwave ports, which includes a TX output, an RX input, and then a shared TX RX port for TDD applications. On the right-hand side of the unit, we see the USB console interface, as well as the 12-volt DC input. So for this demonstration, we're going to use the IF inputs, the external LO inputs, and we're going to loop back the TX output to the RX input. So we'll begin making those connections. Now that the connections have been made, we are ready to configure the device. So to configure the device, first of all, we need to set up our terminal program to connect to it. So we can look at our serial port settings, our baud rate, data, parity. Once all that's good to go, we can make sure we're connected by typing the help command. We see a list of available commands. So in order to configure for this loopback demonstration, we're going to send this text file of commands, which will set up the converters in IF mode. They will set up the gain of the converter, the gain of the IF path for both the TX, RX. It will turn on the PA, and then we'll see our spectrum appear. So we'll send this file to the device. And here we can look at our results in our signal analyzer. So we see our 30 megahertz 5G signal in the top left corner, our 256 QAM constellation. We see our composite EVM at about minus 35 dB. So again, for this, we set up our TX-IF at 2 gigahertz. We're up converting to 24 gigahertz. We're taking that 24 gigahertz signal, looping it back into the receiver input, and then down converting to our 2.3 gigahertz receive IF. So this EVM comprises both the TX and entire RX chains.
During the demo, we witnessed the ease with which the converter can be set up and configured. The script shown on this page represents the list of Skippy commands that were transferred to RadioThorium through the console via USB. Without diving into too much detail, let's look at another example of the protocol's macro features. The first line of the upconverter configuration script above sets the mixer to use the IF input. This is accomplished using the CV mode macro, followed by a minimal set of arguments. The first is the number 0, which targets the converter at address 0. You may remember that our platform supports the use of several converters cascaded together and controlled as a single unit. Therefore, the command needs to be directed to a specific address. The next argument are the characters TX, signifying that the up converter, as opposed to the down converter, is to be selected. Finally, the argument IQ is used to direct RadioThorium to automatically set the switches, filter paths, and programmable gain registers required to support the IF input. We'll now switch our attention to preliminary test results. Our first prototypes arrived in the lab less than 3 weeks ago. All of the critical blocks are functional and characterization is underway. Initial results are looking good, with reasonable correlation to our simulations. On this slide, we can see the frequency response of the down converter. Due to the limited range of our vector network analyzer, the 60 dB of variable gain available in the IF pass was set to 0 dB. For this test, the IF frequency is fixed to 2 GHz and the RF is swept from 24 to 44 GHz. The VNA generates a swept LO signal, which is fed into the external LO port of the down converter. Given that our IF is fixed, we can assume that the frequency responses of the orange and blue traces are dominated by the RF front-end and mixer stages. By varying the RF gain from minimum to maximum, we can also confirm that the converter is providing us with a specified 20 dB of attenuation range. Finally, we can also note that the millimeter wave input port is achieving better than -10 dB of return loss across the entire 24 to 44 GHz range. For interest, we repeat the previous test for a fixed IF of 4 GHz. The slight change in overall gain is due to an increase in the path losses of the IF strip as compared to those at 2 GHz. The return losses remain largely untouched, as those are in the RF section, which has not changed. On this slide, we present a snapshot of the IF output spectrum. For this test, the IF input was set to 32 GHz and the IF to 2.35 GHz. The IF frequency was selected to align with the center of the 100 MHz filter of our filter bank. The blue curve represents the entire 1 to 6 GHz spectrum present at the IF output when the filter bank is bypassed. After enabling of the 100 MHz filter, the resultant IF output spectrum looks like that in the orange curve. The slight drop in signal level at 2.35 GHz is a result of the filter's insertion loss. The spurious-free dynamic range of this configuration is over 60 dBc. Both the up and down conversion paths include an IF filter bank. To minimize size and cost, the banks are realized using off-the-shelf components readily available for 5G radios. As a result, the center frequency for each of the filters varies slightly. This plot compares the frequency responses for the various filters. The observed passband ripple on some traces suggests that improved matching may be required. Close to 30 dB of out-of-band rejection is being obtained. Switching to the up converter now, we begin by looking at the output power as we vary the input. In this example, our IF is set at 2 GHz and an LO is chosen such that we generate an output at 24 GHz. The input power is increased while the output is monitored. Approximately 42 dB of upconverter gain is observed here throughout the linear range of the chain. The compression point can be determined from the plot. At 24 GHz, the output P1 dB occurs somewhere between 19 and 20 dBm. The frequency response of the up converter is shown on this plot. As observed on the previous test, we obtained close to 42 dB of gain at 24 GHz. Due to increased path loss at higher frequencies, the overall gain drops off to about 34 dB at 39 GHz. Over 35 dB of gain control range is observed. Given that the connector, launch, and output switch are the same on this path as on the down converter, we can infer that the return loss at the output is primarily a function of the PA impedance. We'll now have a look at modulation integrity. Our DVD setup for EVM measurements is based on LabVIEW. Control of the converter is accomplished using a console interface over USB using a VI driver that we've developed specifically for RadioThorium. Modulated signals are generated and analyzed using a software-defined radio. For these tests, a 5G waveform is selected, which produces a 30 MHz 256 QAM signal. During our testing, we discovered that noise is being coupled onto our internal LOs. This noise is limiting EVM performance, and design enhancements are planned for the next hardware revision. In order to continue EVM performance evaluation, measurements on the following pages were made using external LOs. The up converter's EVM performance was measured using a vector signal analyzer. By sweeping the input power, EVM performance over output power can be attained. For this configuration, we can see that the best performance occurred between 0 and plus 15 dBm. Below this point, overall noise is starting to impact the signal-to-noise ratio. Above this range, nonlinearities are beginning to degrade performance. It should be noted that no system optimization was performed prior to these tests. Tuning to improve I and Q balance, origin offset, and other system imperfections are expected to further improve this performance. In a loopback test, the up converter output is fed back into the down converter. External attenuators are used to prevent exceeding the maximum input power of the unit. The output power is controlled to maintain a target operating range. This test evaluated the system loopback EVM performance versus output frequency. It's a quick and easy test to help evaluate system performance without the need for external millimeter wave test equipment.
Thank you, Bernie and Lauren. I'll take a few more minutes to discuss about availability and support before we dive into Q&As. As Bernie hinted, we're almost ready to pull the trigger on a board respin and build beta prototypes. Should have material on hand in the next 6 to 8 weeks so we can start testing again. The plan is to have the product released to the market before the June IMS show in Denver. The RFPD part number has been assigned and you have it there on the screen. And once we build some inventory, hopefully by late May, early June, the product will be available for purchase on our website or through the traditional sales channel. As far as support goes, we are collaborating with Analog Devices so we can utilize their Engineer Zone platform to provide our customers with best-in-class technical support. We are in the process of creating a Richardson RFPD page under Partner Zone and where we'll be starting to upload documentation and test data very soon. The plan is to have the RFPD page visible to the engineering community by March. With this occasion, I'd like to thank Analog Devices, communities, and Central Apps teams for their continued support and especially for being so kind to host us on their platform. In the meantime, for any technical and commercial questions, please don't hesitate to email Bernie and myself or both. And with that, I'm going to conclude the presentation by thanking you all for your attention and for taking 1 hour of your valuable time to join our webinar.